Hey everyone, buckle up, because today we're going to dive into something that sounds like it's straight out of science fiction. The holographic principle.
Yeah, it's a pretty wild idea, right?
Wild's an understatement. It's the theory that our universe is basically a giant hologram.
Which is a concept that's been around for a while. And yeah, it's definitely mind-bending to think about.
So imagine this. Everything we see, everything we touch, all of reality, it's all just information.
And that information isn't even stored here in our 3D world. It's like it's encoded on some distant surface, but with one less dimension.
Okay, so you're saying it's like our universe is a projection, like a really, really advanced 3D movie, but instead of being projected from a 2D screen, it's our entire reality.
Exactly. And that 2D screen, it's holding all the information that makes up everything we experience in the universe.
So this isn't just some crazy theory, right? There's actual physics backing this up.
Oh, absolutely. It all comes down to a concept called the holographic principle.
And today, we're looking at a new paper that tries to explain this principle in a new way.
Yeah, it's using this really interesting idea, finite geometry.
All right, you've definitely piqued my interest. But before we get too far, let's start with the basics. What exactly is the holographic principle?
Okay, so in essence, the holographic principle says that all the information about a region of space, all the stuff inside it, can actually be completely described by the information encoded on the boundary of that region.
So instead of needing to know everything about what's inside a certain space, we just need to understand its outer limits.
You got it.
Okay, that's a cool concept and all, but I'm still not seeing the hologram part. How does this connect to the universe being a hologram?
So think of it like this. Imagine our entire universe is a can of soup, right?
Great.
And the label on that can, that's like the distant 2D surface we've been talking about.
Okay, I think I see where you're going with this.
The holographic principle is saying that all the information about everything inside the universe, all the soup, is actually encoded on that label.
So our 3D reality is like a projection of that information, a
Yeah.
cosmic hologram.
Precisely.
But, and maybe this is getting too far ahead, doesn't traditional physics say that a region of space can actually hold way more information inside than on its surface?
That's exactly right. It's a huge question. How can a 2D surface hold enough information to describe everything in a 3D space? And this new paper tries to solve that problem with finite geometry.
Okay, now things are getting really interesting. Tell me more about this finite geometry idea.
So this paper suggests that the universe, contrary to what we've always thought, doesn't have infinite points.
You're saying space isn't continuous.
Right. It's more like it's made up of a finite number of points, kind of like pixels on a screen.
So instead of being smooth, space is more like a digital image with a set resolution.
Exactly. And if you only have a limited number of these pixels of information, you only have a limited amount of information that can be encoded even in a 3D space.
Which neatly solves the problem we were just talking about.
Exactly. There's no longer this issue of 2D surfaces not being able to hold enough information.
So by proposing a universe built on these finite information points, we might be able to explain how a 2D surface can encode a 3D reality, just like a hologram. That's actually a pretty elegant solution.
It really is, and what's even more intriguing is that it could have some pretty big implications for other areas of physics.
Like what?
Well, for example, this finite geometry concept might change how we think about black holes.
The black holes and holograms. Okay, now you're speaking my language. Let's dive into that next. Okay, black holes. Always a crowd pleaser. So what does this paper say about all the information that gets sucked into a black hole if information can't be destroyed?
Right, so black holes are often called information black holes because once something crosses over that event horizon, that boundary of no return, we usually just assume that information is gone.
Makes sense. I mean, nothing, not even light can escape a black hole once it crosses that point, right?
Exactly. But what's interesting is this paper suggests that the information doesn't actually vanish. It's more like it gets encoded on the surface of the black hole itself on that event horizon.
Hold on. So you're saying the surface of a black hole, which is already, incredibly dense, could hold even more information. How's that even work?
Well, remember those finite points we talked about earlier?
Yeah, the whole universe is like a digital image idea.
Right. So those points, when information gets projected from the 3D universe onto that 2D surface, this paper suggests they get magnified. It's kind of like when you take a low-resolution image and you zoom in really, really close. Each pixel gets bigger.
So something that looks gigantic in our 3D universe, it could actually be representing something much smaller on that 2D surface.
That's the idea. And get this. This magnification effect, it could be extreme, especially when we're talking about black holes. The paper suggests that the interior volume of a black hole might actually be directly connected to the radius of the observable universe.
Okay, you're blowing my mind a little here. Can you give me an example?
Sure. Imagine a black hole, not even that big, let's say with a radius of 3 kilometers. Pretty small by cosmic standards, right? Well, this paper, using this finite geometry idea, suggests that the inside of that black hole could actually be bigger than the distance between the Sun and Mars.
Whoa. So you're telling me a black hole the size of a city could theoretically contain a space bigger than our solar system? That's insane.
It really makes you wonder if we've got it all wrong when it comes to distances and sizes in the universe. What we experience as vast distances might just be a trick of this holographic projection.
It really makes you wonder if our perception of the universe's size is totally off. But hold on. If this magnification thing applies to black holes, could it apply to other stuff in the universe too? I mean, what about our solar system?
That's a great question. And yeah, the paper touches on that. If we take this concept and apply it to something like, let's say, our solar system, which is, what, about 9 billion kilometers across?
Roughly, yeah.
This paper suggests that on this holographic surface we've been talking about, the real size, after you factor in all the magnification, would be dramatically smaller.
How much smaller are we talking here? Give me the numbers.
Okay, so according to this paper, if you could measure the solar system on that surface, it would only be about 455 kilometers across.
Wait, seriously? That's like smaller than the state of Texas.
Yeah.
That is wild. It's incredible to think something so vast to us could actually be represented by something so small.
Right. It really does make you think about the universe and what we think we know about it in a whole new way, doesn't it?
It really does. It makes me think about some of the other big mysteries out there, especially ones that have to do with these mind-boggling scales.
Yeah.
You mentioned the cosmological constant problem in your notes, right? Remind me what that is again and how this all might connect.
Oh, yeah, that's a perfect example. The cosmological constant, to put it simply, is this term in Einstein's equations of general relativity, and it basically represents this energy density of the vacuum of space. It's like the energy that's there even when there's nothing else around.
So even in the emptiest parts of space, there's still a baseline energy level.
Exactly. The problem is that when physicists try to calculate this cosmological constant based on what we know about quantum physics, the number we get is way, way off from what we actually observe.
How off are we talking here?
Some calculations, and I'm not kidding, suggest that the cosmological constant should be about 120 orders of magnitude bigger than what we actually measure. It's a huge mismatch.
Okay, yeah, that sounds like a problem. So we've got our understanding of gravity on large scales and then quantum mechanics on the smallest scales, and they just don't seem to line up.
Yeah, and this is where this whole finite geometry idea could really shake things up. If the universe has a limited number of these information points, then its energy density, which is related to that cosmological constant, it also has to be finite.
So instead of having this potentially infinite amount of energy crammed into the vacuum of space, which leads to these insane calculations for the cosmological constant, you're saying this finite geometry idea suggests there's a limit.
Precisely. And here's the interesting part. That finite limit, it might be much, much closer to the actual observed value of the cosmological constant, which could potentially resolve this huge problem.
So this simple idea, the universe being made of finite points, it might actually hold the key to solving one of the biggest mysteries in physics.
It really could. It just goes to show that sometimes the most elegant solutions are also the most profound.
This paper has given us so much to think about. It's like we're looking at the universe with a whole new set of eyes. But before we get too lost in all the possibilities, I think it's time to bring it back down to Earth, or at least to our current understanding of it.
Definitely. Let's recap what we've talked about and try to make sense of what it all means for this idea of a holographic universe.
Sounds like a plan. All right, so to recap, we've spent the last hour going down the rabbit hole, talking about this mind-blowing idea that our universe might actually be, well, a giant hologram.
Yeah, it's a lot to take in. We've gone from thinking about the universe as this almost infinitely vast space to considering the possibility that everything we know, stars, galaxies, even us, it's all just a projection.
Like a cosmic movie projected from some distant surface.
Exactly.
It's kind of dizzying when you really think about it.
Yeah.
So as we try to wrap our minds around all of this, what are some of the big takeaways? What's really sticking with you after this deep dive?
Well, I think the biggest takeaway, the one that really makes you question everything, is that our whole perception of reality, of how big things are and how far apart they are, it might be completely wrong.
Right. It's like the universe is playing a giant trick on us.
Exactly. This holographic principle, if it's right, means that what we see as these huge, vast distances, it could just be a result of how information is projected from that 2D surface onto our 3D reality.
It's like the ultimate optical illusion.
Right.
You talk about how this could apply to black holes, how they can pack so much information into such a small space, but then we took it even further and looked at our own solar system.
And that's when it really hits home, I think. To think that something as immense as our solar system, which stretches billions of kilometers, could actually just be a representation of something just a few hundred kilometers wide on that holographic surface, that's just mind-blowing.
It really makes you appreciate just how strange and how amazing the universe could actually be.
Definitely.
But this isn't just about crazy thought experiments, right? I mean, this holographic principle, it has real potential to answer some big questions in physics.
Absolutely, like the cosmological constant problem we talked about, this idea that the universe has a finite number of information points, that could potentially explain why the calculations for the cosmological constant are so different from what we observe.
It's like this one idea, this finite geometry. It could be the key to solving this huge mystery that's been bugging physicists for decades.
It really could be a game changer.
This whole conversation has just left me with so many questions, like, if the universe is a hologram, where is this screen? And what does it even mean for anything to be real in this scenario?
Those are the million-dollar questions. Unfortunately, we just don't have all the answers yet. It's still early days in this field, and we've got a lot more to learn.
That's true, but that's part of what makes this so exciting. There's so much we still don't know about the universe. And the more we learn, the more we realize just how much more there is to discover.
It's really humbling, isn't it?
It really is. Well, on that note, I think we've given our listeners a lot to chew on today.
I think so too.
To everyone listening, thank you for joining us on this incredible journey into the holographic universe. And remember, the universe is full of mysteries, so keep looking up and keep asking those big questions. We'll see you next time for another deep dive.